When it comes to filtering sequences, the where extension method provides most of your needs. There are also the distinct and of type methods. Distinct gives you a distinct list of all the items in the collection, and of type lets you filter for certain types of objects in collections that contain multiple different kinds of things. But the distinct method is somewhat tricky. Think about it. You have to have a way to compare items in the collection. For simple objects, this isn't a problem. For integers, for strings, those things the .NET Framework can compare without any help. But what about a collection of complex objects? How is it possible that distinct can compare two objects if it doesn't know what they are? In that case, you must provide an instance of a class that implements iEqualityComparer. That interface is there to help you compare two objects in a collection. We'll have more on this a little later in the section. For now, let's look at an example that uses the where clause to do some filtering. I'll choose option J to filter with the where method, and we'll step into this procedure, which again is working with files. In this case, I have a where method call which will filter the list of files down to those where the file length is less than 100 bytes. You can see the lambda expression being passed to the where method here, which indicates we'll only accept files whose length is less than 100. The expression here must be a Boolean value indicating whether or not to accept the file. Once we've filtered the files, the result of that filter is sent to the select method, which projects the resulting data in a formatted string, displaying the file name and then the file length in parentheses. Let's try that. And you'll see in the output window, we get a list of all the files whose size is less than 100 bytes, displayed as file name and then in parentheses the file size. Just as you can with the select method, with the where method, you can pass a lambda expression that accepts two parameters. The second parameter indicates the index of the item being checked, the index within the original data. So here, we're looking for files whose length is less than 100 and appear within the first 10 files in the input to the where method. This time, we'll probably end up with less than 10 files in the output because in this case, we're only looking within the first 10 files. Get the same projection of the output of the data, and you'll see we see only a single file in the output because within the first 10 files coming into the where method, only one was less than 100 bytes. So we've used the where method using two different lambda expressions. The first passes in an expression to check for, and the second passes in the expression and an index. In terms of ordering sequences, there's really nothing new here that you haven't seen already. There are 4 helpful methods you can use for ordering sequences, including order by and order by descending. Those order the data in ascending order and descending order. If you want a secondary or third level sort, you can use the then by or then by descending methods. And in each case, you supply an expression, a lambda expression, that indicates how to perform the sorting. But you've seen examples of those already. How about verifying sequences? You might want to determine if a sequence contains any elements or if the sequence contains any elements that meet a condition. There's the any method that does that for you. You might want to know if all elements of a sequence meet a condition, and there's the all method for that use. You might want to know if a sequence contains a particular element, and there is the contains method for that need. And you might want to know if two sequences are equivalent, and for that, there's the sequence equal method. Now, the problem here is you're going to be comparing elements within a sequence. And for complex elements, the .NET Framework doesn't know how to compare them. Say you're comparing two customers. What makes two customers equivalent? You'll need to indicate that information to the .NET Framework. And in that case, you'll need to use an iEqualityComparer instance. You'll need to create a class that implements the iEqualityComparer interface to indicate how to compare two instances of the type, And then, when you want to perform the comparison, supply an instance of the iEqualityComparer class that you've created so your code knows how to compare those things. Well, that's a lot of talk. Let's look at an example that shows how you can use these methods and the iEqualityComparer interface. Because we'll be comparing two product instances, I've created the Product Comparer class here. I've put it in a separate file to make it easy to find, and you'll see here we have a Product Comparer, that's the name I gave it. It implements the iEqualityComparer of Product generic interface. When you create this class and implement that interface, you need to supply these two methods. If you've never done this before, here's what it would look like. We'd say class X implements iEqualityComparer. We'd say of product. There we go. And here's our class. Now if we right-click on this line, we have an option to implement the interface. When we implement the interface, you see the two methods that you must implement to provide the implementation of this interface. There's the equals method and the getHashCode method. By default, these have exceptions thrown from within them, so if you try to use them without providing code, you'll know. I've already done this, so let me get rid of this class and go back to my original class up here. In the equals method, you need to indicate how you would compare one instance to another. And for a product, that means comparing product IDs. And in this code, all I did was say, given two products, X and Y, I'll take x.productId.equals y.productId and return that value. It's easiest when you're implementing the equals method to just call the equals method of the two things you're trying to compare. In our case, it's product ID. For the getHashCode method, this is used so you can identify an instance, a particular instance of the object, and for most objects you can just call the base class's getHashCode method. You may want to implement your own code in getHashCode, and there's lots of documentation on how you might do that. For our case, since I'm only using this to compare two instances, using the getHashCode method of the base object class is really good enough. But you'll often need to write your own code there. But in our case, all we need to do is compare two instances, and so this equals method, comparing the product ID of one to the product ID of another, is all we really need to care about. Let's look at the verifying sequences demonstration code then. That's option K. Let's go to full screen. Here we are. And I would like to first retrieve some results. So here, I'm taking the products list and filtering it down to those where the product is in category ID 1. There we go. And now we have a list of every product in category ID 1. It looks like that. There's everything in category 1. All right, let's now determine if the list has any elements. Well, we know that it does. When you call the any method with no parameters, it simply returns a Boolean indicating whether there are any elements in the collection. And of course, that will be true. Yep, there are some elements in that collection. Now let's work with discontinued products. The way we do this is determine are there any that are discontinued. We take the any method, pass in a lambda expression, and the lambda expression tells it what to check for. It's a where clause. And any will return true if filtering with that where clause returns any values. So in this case, we're checking to see, given our results, that is all the products in category 1, are there any where the product.discontinued field isn't false? Are there any discontinued? Let's see. There are some that are discontinued. Okay, that's easy enough. Let's now look for products that start with M. Well, were there any? Let's look. No. So if we come back over here and say, let me get results.any, passing in a lambda expression that checks to see for product.productName.starts with M, and we'll use that as our filter for the any method, you'll see that there are none that start with M. Okay, let's use the all method. Is it true that all products have at least 5 units in stock? Well, the all method also takes in a lambda expression. In this lambda expression, we're checking for prod representing a product, and we return true if prod.unitsinstock is greater than or equal to 5. What all does is loop through all of the items in the input collection and return true if all of them meet this condition. Is this true? Let's see. It's true. All of our products have at least 5 units in stock. Okay, now let's check to see if our collection contains a given product. Now we know that we're only using the product ID to determine if 2 products are equal. And to use the contains method, we'll need to supply a product comparer to compare products to see if one is inside the collection. So here we'll create a new product, I'll call it item, and I'll make it have a product ID of 1, and I'm setting the product name even though I'm not using it anywhere, just so I know what it is. Here I'll check to see if the results contains our item. Now, if I just called it without a product comparer, the code would fail because it has no way to compare to see if our list of products contains a product whose ID is 1. On the other hand, if I pass in a product comparer instance, I do by creating a new instance of the product comparer class, the one we just looked at, remember, that implements equality comparer, that has an equals method there. Here, if I pass an instance of that class, it knows what to use to perform the comparison, and we'll be able to see if that item appears within our list of products. And it does. Oops, we're not quite there yet. And it does. Of course it does. Here's product ID 1. We asked if product ID 1 exists within the collection, and it does. So you've seen now using that product comparer to perform a comparison so we can determine if an item is in the collection. Now don't get confused by the fact that when I created the new product here, I only initialized a few fields. Often you'll have all the fields filled in for your product or whatever you're looking for. In my example, the only thing I had to have was the product ID. So I had to create a new product whose product ID was 1 and use it for my search. I've indicated only the fields I needed, but I could have had more fields filled in. That is, I could have taken a product from a real product somewhere and say, does this product exist within this collection? I've shortcutted here and only supplied just the fields I need for this demonstration. I didn't mention that if you want to compare 2 sequences and see if they're equal, you can use the enumerable.sequenceEqual method. But just as you did when checking to see if a sequence contained an item, you'll need to supply a class that implements equality comparer in order to compare 2 sequences that contain complex objects. If you want to convert a sequence to another type, you can use one of these methods. There's the toArray method, toDictionary, toLookup. There's the cast method, which we've used in an example, and the asEnumerable method. The asEnumerable method returns the input sequence cast as an IEnumerable of some particular type. You might want to position within a sequence. Given a sequence, maybe you want to skip over some elements, then take a subset of the elements, like skip ahead 20, then take 5. You can use any of these methods. There's the skip method, which skips ahead a certain number of items. There's the take method, which takes a certain number of items. There's skip while, which skips ahead through a collection while some condition is true. And then there's the take while method, which takes items from a collection while some condition is true. Let's try some examples that show off converting sequences and positioning within sequences. To demonstrate converting sequences, I'll choose option L. Here we're going to take a sequence, that is, all of the products, in category 2 anyway. There we go, all the products in category 2. Oh, I did want to mention that you can write this query in multiple ways just to relieve any anxiety about functional syntax versus query-based syntax. Here's using functional syntax with a lambda expression. Here's using the query syntax. Either way, we're taking all the values in getProducts and only returning those where category ID equals 2. All right, so that's our input. Now I'd like to, here's the goal, get myself a comma-delimited list of all the product names. Let's start in the middle of this expression. I'll take products and call the select method to perform a projection. I'm indicating that I want to take the products and return only the product name for each product. There's a lambda expression that does that work for me. Then I'll take those results and convert them to an array. The toArray method will hand me back an array of strings. Now, since I wanted a comma-delimited list of strings, product names, the string.join method is the easiest way to get that. So I pass this array, which I just got, as the second parameter to string.join. String.join takes as its first parameter a delimiter, and as its second parameter an array of strings to join together using that delimiter. And so when I call that method, I end up with a comma-delimited list of product names. Pretty clever, huh? It's great being able to mix and match technologies like this. Now, say you wanted to have a dictionary of products in memory using the product ID as the key. Remember, a dictionary is useful when you want to store items in memory and have instantaneous access to any single one of them, or nearly instantaneous access. Putting them in a dictionary using something that's unique as the key makes it quick and easy to retrieve information about a particular item in the dictionary. Here I want to use the product ID as the key. The toDictionary method allows you to specify, it actually requires you to specify a lambda expression that identifies what becomes the key for each item in the input sequence. Now, there are multiple overloads for toDictionary. You can also provide, for example, a lambda expression that lets you identify what becomes the value in the dictionary. In this case, we want to just use the product as the value, so I'm only specifying a lambda expression that will identify the key. When I perform that conversion, we now have a dictionary containing, well, as a key, the product ID, and as a value, the product itself. A dictionary contains a collection of key-value pairs, and here I'm going to loop through that collection of key-value pairs, and for each key-value pair in the dictionary, I'll write out the key, which will be the product ID, and the value, that's the product itself, I'll retrieve the product name. So here we'll display, in a formatted fashion, all the items within that dictionary. You can see for Category 2, here are the items in the dictionary, and we could retrieve these quickly using the product ID. That's how a dictionary works. You've seen in this example how to convert a sequence into an array, and also how you might use that array. And you've seen how to convert a sequence into a dictionary using one of the properties of the items in the sequence as the key for that dictionary. To demonstrate positioning within sequences, I'll choose option M, and here we'll try a couple of different ways to do this. First of all is a technique we really haven't used very much in this course, and that is mixing the query syntax with the functional syntax. Here, if you look inside the parentheses, I have a query syntax that describes what I want. I say from prod and get products, so I'm looping through everything in the get products collection, order by product name, select, so I project the data as a single string with product ID : product name as the contents of that single string. That becomes the input for what follows. So I have parentheses around that whole mess. You can see them there. There's the output outside parentheses. I take that and then say .skip10, .take5. .skip10 says take that input and skip over 10 elements, and then taking the same input where we are in it, take 5 starting there. Another way to do it is do the whole thing using the functional syntax. Here I say get products dot order by. Here's a lambda expression that indicates how I want to sort. Dot select. Here's a lambda expression that indicates how I want to project the data as a single string. Dot skip10. Take 5. So either way, we get the same exact results. We're going to take the entire list of products, start at the beginning, skip over 10 items, and starting there, take 5 items. And if we look at the results, you'll see we'll end up with the 11th through the 16th items within the list of products. We skipped the first 10 and then took the next 5 from where we left off. You'll find skip and take, and skip while and take while, useful for positioning within an ordered list of items. You might want to perform calculations in sequences. For example, you might want to calculate the average, the count, the max, the min, or the sum of a sequence. There are functions that provide all of these mathematical calculations. For each of these, you can supply no parameter which works on all the elements in the sequence, or you can supply a lambda expression which modifies the behavior of the method. And before I look at a demonstration, I will mention that though we're not going to look at it, you can also use the enumerable.long count method for large collections. If you have more than an integer's worth of items in a collection, a lot of items, you'll need to use the long count method for that large collection. Let's look at an example that demonstrates calculating within sequences. For these simple calculations, I'll choose option N. We'll step into our code here. And let's start then by getting our products. I store it in a variable so I wouldn't have to call getProducts multiple times. That's the only reason. Let's select the unit price and get that into a sequence. Given our sequence of decimal values, let's calculate the average. So what we have right now is just a sequence that contains a single item, which is the unit price. And given that, well, column of unit prices, we can calculate the average. No problem. On the other hand, you might not want to create that column of averages first. And by the way, we did get an average. There it is. You might not want to create that column of unit prices before calculating the average. Given our entire list of products, if you just call the average method, how does it know which column to average? Because of that, you need to provide a lambda expression, as I've done here, which indicates which column we want to average on. So for the average method, if your sequence contains more than a single column, you need to supply a lambda expression that indicates on which column you want to average. So here we've specified that as a lambda expression, and we should get the exact same value. We did. The count method, on the other hand, can count the list of products no matter how complex they are, and so we just call the count method without any parameters. It returns the count of products. Now, of course, you might want to provide the count of a filtered list, and to do that, you can provide a lambda expression which defines which products you want to count. In this case, the lambda expression indicates that I only want products with a product name that starts with B. That lambda expression returns true for every product that meets that criterion, and the count method will count them up. We should have, well, 1 that starts with B. You can use the max method to determine the maximum of any given column, but again, these are complex items in this sequence, so we have to indicate which column we want to search in. So here I have a lambda expression which identifies the unit price column is the one in which I want to look. So we'll retrieve the maximum unit price, and that is 263.5. Okay. We can calculate the sum of units in stock. And again, because we're summing a column within a bunch of different columns of products, we need to know which, well, property in this case, we want to sum. Again, we pass a lambda expression which indicates which item we want to sum, its units in stock in this case. So we can sum that particular property and find out the sum of units in stock is a specific value. Now, these methods, max, sum, and others here, allow different overloads so you can supply where clauses and other information. I've just showed some simple examples in this demonstration. You've seen how to use the basic calculations, count, sum, average, min, and max. But what if you need to aggregate data in your own way? There is an aggregate method which applies an aggregator function over a sequence. You just have to provide the code that does the work. Let's say we would like to calculate the standard deviation of the unit price value in our products list. To do that, we need to calculate the average unit price. Then calculate the sum of the squares of the difference between the unit price and the average unit price. That sum of the squares of the difference helps us calculate standard deviation. Next, we'll calculate the variance, which takes the sum of the squares values we calculated in the previous step divided by the count, the number of unit price values. And finally, to calculate the standard deviation, we take the square root of the variance. It's kind of a complex calculation. Doesn't really matter if you care about standard deviation or know how to calculate standard deviation. The only point of this demonstration is to show that you can do this sort of complex calculation over a sequence using the enumerable dot aggregate method. I will point out there are multiple different ways to calculate standard deviation. I picked one that was simple to use. You might have more complex ways to do it. Feel free to rewrite this demonstration using that more complex standard deviation code. Let's look at an example that shows off how to perform this calculation. To test out that aggregate method, I'll choose option O. Here in our code, we'll start by limiting our products to only those in category 1. So I've passed in a where method call with a lambda expression that indicates I only want the products where the category D equals 1. Okay. Now, in order to perform the calculation of standard deviation, I'll need to know the average unit price value. To do that, I'll take results.average, and for the average method, I'll pass a parameter which is a lambda expression, which identifies which property to use for calculating that average value. We'll calculate the average of the unit price, and we'll store that value away into a variable. Now the complicated part, to calculate the sum of the squares. In this case, we'll call results.aggregate, and the aggregate method requires at least 2 parameters. The first one indicates the starting value for our accumulator. We accumulate sum of squares and we start at 0. The second parameter is a lambda expression that accepts 2 values. The first value indicates the current value of the accumulator, and the second one is the current item to be added to the accumulator. So how do we perform this calculation? Remember, we're calculating the sum of the squares of the difference between the unit price of an item and the average unit price. So here's how we do it. For each item, we want to take the current value, that's our current accumulator, add to it this expression. And this expression is, we're taking math.pow that raises a value to a power. We're converting the difference between the unit price and the average price to a double. We're raising it to the second power. That squares it, and converting that result to a decimal so we can add it into this current value. All we're trying to do is take the old current value and add in the square of the difference between unit price and average price. We keep doing this for each item in our collection. That's what the aggregate method does. You supply a starting value and a function to call to increment your accumulator. The accumulator will be its current value plus some new value, which we calculate here as the square of the difference between the unit price and the average unit price. Well, that's the aggregate method. Once we have that sum of squares, which is some big number, the variance is the sum of the squares divided by the count of items in the collection. Now, of course, this is stupid math, because if the collection currently contains 0 items, this would raise an exception, and we might want to check for that first, but I didn't. So we'll get the variance, which will be, in this case, 4716 dot something, and the standard deviation, which is the square root of that value. So again, we call math.pow again, using the 0.5 power, and we get the actual standard deviation. I'm sure you're dying to know what the standard deviation of unit price is, and there it is. Now you can use the aggregate method on non-numeric types as well. Imagine that you want to create a comma-delimited list of product names. We've already seen one way to do this, but the aggregate method can do it as well. First thing we'll do is project our list of products into just a list of product names using results.select and in the select method pass a lambda expression which identifies the field we want to project, and in this case we'll use product name. So product names just contains a sequence of strings. We can use the aggregate method. We'll take product names dot aggregate, and just like before, the first parameter indicates the starting value for our accumulator, string.empty in this case, and then the second parameter is a lambda expression which has two parameters. The first is the current value of the accumulator. The second is the current value we'd like to add to the accumulator. It's up to you to control what you do with that accumulator and the current value. Well, in our case, for the first item, where the current accumulator is an empty string, we want to just put the name out there. On the other hand, for all the rest, when the accumulator isn't an empty string, we want to take the current value of the accumulator, add a comma and a space, and then the current name. Here's how you do it. You use this ternary operator which says if string.isNull or empty, that is, if the current accumulator is null or empty, just use the name. Otherwise, take the current accumulator, add to it a comma and a space, and then the current name. We should end up with, if we've done this right, a comma-delimited list of all the products in category ID 1. And there we are. We get our comma-delimited list. A different technique, that's for sure, but we still end up with that comma-delimited list of strings. To finish up our march through all of the different methods provided by the system.LINQ.enumerable class, we'll look at set operations. There are a number of different methods that allow for working with sequences as sets, including the concat method to concatenate two sequences together, union, intersect to find where two different sequences intersect, there's except to find items in one sequence that aren't in another, there's join, group by, and group join. We won't look at those in this example. We'll look at some of those later when we discuss working with data. For now, though, let's look at an example that demonstrates several of the methods that allow for set operations in sequences. I'll choose option P. This will let us investigate various set-oriented methods. We'll first start with an array of state names and a second array of state names. Now here, just to keep track of what's in which group, we'll display each of them in our output window. And you can see that if you look at this carefully, there are some overlaps between these lists, and each list has some items that aren't in the other list. Memorize those lists quickly. Here we go. Now I'd like to concatenate the two lists. We can call group1.concat, and we can supply as a parameter the group we'd like to concatenate to group 1. This ends up with group 3 as our resulting group, and we display it. You see, it has all the items from group 1 and then all the items from group 2 concatenated together. There are repeats in there. Now let's try the union method. Union is a smarter concatenate. It removes duplicates. So if we try group 1 union group 2, we end up with now only the unique items in the two lists. That's an interesting method because that can be helpful at times. The intersect method allows us to find all the elements that are in one group that are also in another group. Now, because we'll need to compare items to make this happen, if you're working with a complex object in your sequence, you'll need to provide your custom I-equality comparer instance to compare items. But for strings, as in this demonstration, we don't need to do that. The .NET Runtime can perform the calculation for us. Here I'll show the intersection between group 1 and group 2, and you'll see the items that are in group 1 that are also in group 2. Finally, the except method finds differences between group 1 and group 2. This returns the set of all the items that are in one group but not the other. Let's try it. Group 1 except group 2 gives us all the items that are in group 1 that are not in group 2. So you can use these methods to return various information about sequences, treating them as sets, looking for the union, the intersection, and so on.